it's also, I get back what I started with. Right. Okay, so yeah, that's for pairs. So the point here to remember for the topic of this lecture, because there's only one constructor, typically definitions of functions that operate on pairs only have one equation. Now lists, we talked a bit about lists yesterday already, and we mentioned that they have special syntactic support. So they also have two constructors, the empty list and the non-empty list, which, I mean, you can call it the cons case, but that's like historically from Lisp, I think, whatever. So where list is either empty or it's a head and a tail, where the tail is again a list. And we can already guess, because there are two constructors, that functions operating on lists will have, often will have two defining equations, one for the empty list case and one for the cons case. So this is just that. And this is now the first example today of a recursive type. I mean, yesterday we already had our chain type, which was recursive, and we talked about lists. But bool, maybe, and pairs are not recursive. But lists are recursive. Here in the second constructor, the list appears again as an argument. So it's a recursive data type. And typically, functions operating on lists will also be recursive. Because, I mean, not always, but typically, because here in the second case, in the cons case, you have the tail of the list, which is again a list. So it would make sense, syntactic sense at least, or type sense, to apply the function you are just defining to the tail. And often, very often, that's the case. So recursive data types tend to lead to functions that are recursive. And as an example, I mean, we saw that yesterday already, but that was, we saw the prelude version. Maybe let me hide that as well. And let's just, I mean, yesterday I briefly, I mean, we saw this foldable type class without explaining exactly what it is. I just said it's a container. So the length in the prelude is more general, but let's just implement it on lists. So we have our two cases. We must say what is the length of an empty list, and that's 0. And we must say what's the length of a non-empty list. Well, and we know that probably it will be a recursive function where we apply length to the tail. So given the length of the tail, what is the length of this list? Well, it's one more than the length of the tail, because we have this additional x. And now it's probably complaining because I don't need the value of x. Yes. We can try that out. And we get our 5 again. Recall, string is a list of characters, so I can apply length to it. Right, so length is one example. Next example, lm, we saw that, but let's implement it. I mean, I used it already in my example somewhere. Let's hide that as well. So given an A and a list of A's, return a Boolean. So the function is supposed to check whether the given A is in the list or not. Right. This is wrong now, but I'll fix that in a second. So we won't be able to implement this, but right. So because it's a function on list, we try the standard pattern. So two equations, one for the empty list, one for the non-empty list. So in the case of the empty list, we know the answer is false. X can't possibly be in the list because there's nothing in the list. And we don't even need to know what X is. Now in the case of a non-empty list, So what can we do? We do know that probably it will be a recursive function, so at some point we will check whether our element x is in the tail. But so what do we do with the y? Well, if x equals y, then we are done. Then we don't even have to look in the tail, then we have found our element. But if not, then we recurse and check the tail. And now, of course, the problem that I mentioned, so I mean, we check whether x equals y, and if, or alternatively, we look in the tail. And now that doesn't work because I'm using this equality operator, but I haven't said anything about my type A, so compiler complains because it doesn't know whether I can compare two A's for equality. So I need an A constraint. And why is it? Oh yeah, this is a precedence thing, I think. Yeah. So there was some operator precedence clash between the equals and the disjunction. Therefore, I needed parentheses. Okay, and now we can check out whether it works. So lmy Kenya is true, but lmq Kenya is false. Right. What's the next example? Okay, so appending two lists. It's also, as we saw yesterday, as an example already built defined in the prelude. Let me hide that as well. And let's define our own version. Concatenation of two lists. So following the standard pattern, we must say, how do I concatenate something to the empty list and to the non-empty list? So if the first list is empty and I have a second list, well, then the concatenation of the two is just the second list. And if the first list is not empty and I know, I probably, because of this, how this works, probably somewhere I will recurse and see what the tail concatenated with the second list is. So how do I use this intermediate result to get the final result? Well, I just have to cons x to it. If I have a head and a tail and a second list, I can first concatenate the tail with the second list and then put my original head in front of the result. So we can try that as well. And it seems to work fine. Okay, reverse, that's, well. Sorry. Okay, so reverse A to A, A to A. So just reverse a list again. So let's just do it. So how do I reverse the empty list? Well, that's just the empty list. And how do I reverse a non-empty list? If I can use the result of reversing the tail. Well, and if you think about it, so you have a list, a head and a tail. You know already by recursion what the tail reversed is. So how would you get the reversal of the full thing? Well, you must put the head all the way at the end. So now that we have defined this plus plus, one way to write this would be like so. We can try this out. Okay, that works. But I should say that in this example, I mean, this would be a bad way of writing this. I mean, it works, it's correct, but it's inefficient. It has quadratic complexity in the length of the list, and there is a way to do this in linear time instead of quadratic time. So that's, I think, is topic of one of the exercises, if I remember correctly. Yes, so the moral of that is just that even though this is a very common pattern on lists, it's not always the right choice. Okay, and filter, also saw yesterday. So given a predicate on lists, on elements on A's and a list of A's, return a list of A's that only consists of the elements for which this given predicate is true. Again, pattern matching on the list, so we split cases on the list argument. So two cases, empty list, non-empty list. So if we have the empty list, then there are no elements to keep to begin with. So the result is just the empty list. And we don't even have to care what our predicate is. And if we have a non-empty list, well, then it depends. The predicate could be true or not true for X, for the first element. And this is like a typical example where you probably would use a guard. So the first case is that the predicate holds for X. And in this case, we keep the X. And what about the X's? Well, there we can recurse. So, and otherwise, sorry, just bear with me. And otherwise, we don't keep the X, so we immediately recurse on the tail. We can try this out as well. Okay, so we can, for example, filter is lower Kenya. It only keeps the lowercase letters, or is upper. It only keeps the uppercase letters. Right. Probably map as well. No. Okay, so that's enough examples for lists. Questions?
Makes sense. Could you go into like a step by step? Like how the reverse function is?
The reverse function, yeah. So we have two cases. We must know how to reverse the empty list, and we must know how to reverse a non-empty list if we already know how to reverse the tail. That's this recursion. So the empty list is easy. So, I mean, empty list, there's nothing to reverse, so it's just the empty list. Now, if we have a non-empty list, and we somehow, because we are allowed to use recursion, so we can apply reverse to the tail. So if you just look at it, I mean, if you have, for example, Haskell, the string Haskell.
Maybe 1, 2, 3.
Maybe 1, 2, yeah.
Yeah, you're going to go step by step.
No, I just wanted the top case. But fine, I can also, it doesn't matter. Let's say I have the list 1, 2, 3, 4, and I want to reverse it. So this is a non-empty list. So that would be the second equation. So it's 1 is the head, and the tail is 2, 3, 4. And we can do the recursive call, so we can call reverse on the tail. And what is reverse of the tail? What's the reversal of 2, 3, 4? Well, it's 4, 3, 2. But what do we want? I mean, we want to reverse 1, 2, 3, 4. So the result of reversing 1, 2, 3, 4 is 4, 3, 2, 1. So given that we already know how to reverse the tail, how do we get what we want? Well, you have to squint a bit, and then you see this is just the reversal of the tail. but then the head goes all the way to the back. And this here is just 432 concatenated with 1. And this 432 is just, as in the line above, the reversal of 234. So in order to reverse a non-empty list, I reverse the tail and append the head right at the end. Yeah?
Maybe it will be easier to understand if we just replace what the, in theory, GHC does, like the definitions in each step, like just for 1, 2.
Yeah, or let's say for 1, 2, 3 maybe.
Reverse 1, 2, yeah, reverse 1, 2, 3. Then
okay, so let's do, yes, so reverse 1, 2, 3. So that's the non-empty case. So it's just plugging in the definition. It's reverse of the tail, 2, 3, plus the head.
He pattern match the second definition and he just replaced the right hand side.
Yes. So now we have to compute reverse 2, 3. That's again a non-empty list. So it's again the same equation. So we must reverse the tail. The tail in this case is 3. And append the head. And of course our original thing. So now again, 3 is still a non-empty list. So again we must apply the second. So it's reverse the tail. The tail of the list only containing 3 is the empty list. So we must reverse that and append the head, which is 3. So then our 2, our 1, I think it's right. I just don't know how to align it properly. Yeah. Ah, okay. Okay, and now finally the empty list is the base case. So we know what the reverse of empty list is. It's just the empty list. So we can replace that with the empty list. And I hope I now don't have to convince you that this is 3, 2, 1. I mean, we could do the same. We could plug in the definitions of append, of the plus plus, and calculate that is 3, 2, 1. I mean, it's the same thing. You can do that as an exercise. Try to prove that that is indeed 3, 2, 1 by plugging in the definition of plus plus like millions of times. Okay? Okay, and there you can already see why this is not a good implementation, because this is like, yeah. Anyway, other questions for lists? Okay. Now this is like not standard. I mean, all the types we have looked at today were like standard Haskell types that are in the prelude. So they are always available. This is now not a standard, although I think there's some support for it in the prelude as well, or in data.list, but it's not very common. So, and in particular, this table name, this is like not prelude or standard libraries, that's just this course. So the idea is, I mean, we want a simple lookup table, a key, like a hash map or a dictionary where the type of the keys is k and the type of values is v. I mean, this is also a bit of like matter of taste or convention, how you name your variables or your type variables. So normally, I mean, what I did just now was ABC and so on. But in a case like that, I mean, it's common to use it k and v because it's key and value, and then it's easier to remember which is which. So, I mean, you can, of course, name it whatever you want to name it, but there are like certain conventions. We could also use, I mean, it doesn't have to be single letters. You could also use it key and name it key and value, as long as it's lowercase. Right. So the idea is to model a simple lookup table just as a list of pairs, of key value pairs, which of course is very inefficient for long tables because you always have to go through all the entries until you find the one you're looking for. And of course, Haskell provides much more efficient data structures for this. Okay, and does he implement all of this? Oh, yeah. Okay. And we want this interface to work with our tables. So we want to be able to construct an empty table. We want to, given a key and a value, want to be able to insert it into a table. Given a key and that we can compare keys for equality, we want to be able to delete a key from a table and the corresponding value. And lookup, given a key and a table, we want to find the associated value if it is in the table. So this is a typical use case for maybe. So here the idea would be if the key is not in the table, we return nothing, and if it is in the table, we return just the value. So we want to implement this now. Oh yeah, and one important thing here is to note that in many other languages, the signatures would be different. I mean, for example, insert maybe would be a method on a table class or whatever, and it wouldn't return a result, and inserting an element would change the table in place, or delete would change the table in place. In Haskell or functional languages in general, that's normally not how it's done. So normally persistent data structures are preferred, where you keep the original table as it is and return a new table that now, in the case of insert, has the inserted element. In the case of delete, has the element deleted. So you don't change anything in place. You return a new data structure that's modified somehow. And that sounds horribly inefficient and memory hungry, but it is not. And there will also be a lecture about why not. Okay, let's implement these things. So empty, I must define the type. So type table KV is just a synonym for lists of pairs of K and V. And now empty. Well, what's the empty table? It's just the empty list. No key value pair inside. What was the next one? Insert. So given a key and a value and a table, produce an updated table with this pair inserted. Let me just, there are now several choices. I just want to, yeah. There are several choices what you can do. The question or the problem is, what do you do if this key is already in the table? Do you remove the old value, or what do we do? And in this lecture, what we do is we don't care whether it's already in the table. So we just insert the new key value pair right in the beginning of our list. So it could be that this key value is already there, but we don't care. There would be other choices. You could try to remove that if it also is already there. Now we can already try it out. So what could we do? It's always so painful with the type. Okay, let's say Haskell true. Well, let's start small. So into empty. Why not? Okay, we start with the empty table, and the type of this thing is, so this is a table string bool, so the keys are strings and the values are booleans. You can think it's it's representing good programming languages or whatever. And now I can, for example, do insert Java false to this thing. So now I have Java false, Haskell true, and whatever. And I could now do Haskell again, but I don't want to do Haskell false, but I can do another Haskell true. Or I could do a Java true. No, that's also bad. I do another Haskell true. So this is what I mean with duplicates, so we don't care. So now the key Haskell is there twice. But the convention will just be for this lecture. I mean, this is also not important. It's just an example. You would not use that in production. But we will just say that the first value matters. So basically, the first one is now shadowing this one. OK, so this seems to work. What else did we have? Delete. So delete. And for that, we must have equality on keys. So if you can compare keys for equality, and we have a key and a table, then we return another table with that key deleted. And here again, we have several choices. Do we only delete the first occurrence or all occurrences? And I think the choice made in the slides is only, it's all. So we delete all occurrences. Right, so now tables are just lists. So we have again two cases. I mean, so what we said about lists before equally applies now. So we have two cases: the empty table, the empty list, and the non-empty list. So if it's empty, then there's nothing to delete. I mean, there's nothing in there anyway. So it's just the empty table, and we don't care what the key is. And if it's not empty, now, I'm sorry? Yeah, but yeah, I was wondering whether I should call it K prime and V. KV something. Right, so this is now a little bit more complicated pattern match. I mean, I could do it in several steps, but I mean, first I pattern match on the list, so it's the cons case. And so I have a head and a tail, and now I also pattern match on the head because I know the elements are pairs. So the pairs look like pairs of two variables. So now in one step, I basically do the pattern match on the list and on the pair. So you can nest patterns. It's a so-called nested pattern. Anyway, and now there are two cases that the K prime equals the K or does not. So I can do a guard again. And this is now allowed, the quality comparison, because I have my constraint that K can be compared for equality. So what do I do in this case? In this case, I must delete this first entry. And I mean, I could stop, but we just said we want to delete all occurrences of that key. So that means I drop the first pair, this K prime V, but I recursively also delete K from the rest of my table. Okay, and the other case, K prime doesn't equal K, so I want to keep this pair I have there in the head. And again, I recurse over the rest of the table. So now I can try this out. So if we take this example table again, and I delete Haskell from it, then only Java is left. So it has found the two occurrences of the key Haskell and removed it. If I instead delete Java from it, it keeps the Haskells. And if I delete solidity from it, then it keeps everything because the key solidity doesn't occur in the table. Right, what was next? Lookup. We have insert, we have delete, so lookup is. Okay, lookup. So again, we need to be able to compare keys for equality. And we return maybe a value if we find it. So again, two cases, empty table, non-empty table. If it's the empty table, we obviously can't find the key because there's nothing in the table. So we have no choice but to return nothing. And if it's not the empty table, then again, it depends. So we check whether the key at the head whether the key at the head equals the key we are looking for, and if so, we are done. We have found a value with that key, so we can return just v. And if not, we just recursively look in the tail. And this is probably some prelude thing, yeah. So lookup is defined in the prelude. So I hide it. Right. Okay. And oh yeah, we don't need the key in this case, so I can replace it with an underscore. Okay, let's see. So we have our, our list. And now if I do a lookup for Haskell, I find the value true. If I do a lookup for Java, I find the value false. If I do a lookup for Solidity, I don't find it. So it's a nothing. Okay. Blah, blah, blah. That was that. Okay. Sorry, I just want to see what's next. Okay. Right. So until now, yesterday we already saw two ways to define a new data type in Haskell, or new name of a data type in Haskell. One was the data keyword, one was the type keyword. So data defines a truly new type. And you can given by its constructors and the constructor arguments and so on. So chain was the example for that. And type is just a synonym. So yesterday we had this capital TXS, which was just a synonym for int. And today, just now, we saw this table definition, which is just so table KV is just a synonym for pairs of keys of pairs. Yes.
So in the delete function.
Yes.
I don't know if I'm correct, but I'm assuming when you deleted, you got a copy of the list without what you deleted, right?
Yes, I'm building up a new table. So the old table stays as it is, and I'm returning a newly built table with the element deleted.
So in the case of the real world case, where you're writing to a file, how would you handle that? Because you want to affect the actual file.
Right, so if you have your table in a file.
Yeah, if I have my table in a file, I would need to then later overwrite the file with the return value. I mean, I wouldn't directly in place manipulate it. I mean, I get the new table, and then in the end I write the new one to the file and overwrite the old one.
So we change the function.
No, I mean, the function stays as it is, but I mean, there's no mention of files anywhere. But if I now want to use this function to, I mean, let's say I have my table serialized in a file, and I want to write a function that reads the table from the file, deletes the key Java, and writes it to the file again, then I would have to do it like that. So I would, like 3 steps. I read it, then I apply the function, and then I write the result of the function back to the file.
you wouldn't modify this one because this one is agnostic of where the information comes and where it goes. So you can just plug and play, plug that function. If you have a database, if you have a file, doesn't matter. You have this interface that maybe read file, read database, get the table, pass it to the delete, and then another separate function to read. So then in that way, each function has its own like separate concern. And on top of that, you get to keep delete a pure function that you know like it behaves perfectly. And you have these ugly, like impure functions on the side, in the extremes, right? So you,
It's like you got the other function that is calling this.
exactly. Yes. And we're going to see how to, it's like Lego blocks. We're going to see later how you can compose them. So it's like you will like, click a bunch of little functions to create a huge function.
Mm-hmm. Right, so we have seen two ways to define new, yeah, sorry, yes.
So, like, is it possible maybe you create a variable, maybe named languages, then you, instead of having to call the function every time everything inside, you look up solidity, the variable languages.
Yes, sure, I could, I mean, I had this example, and I could just do let languages equal this, and now I can do whatever lookup. Yes, I mean you can give name to things. In the REPL with let, and in code you don't even, I mean it depends. If it's on the top level, I mean I could also do this.
I think with the latest version you don't need the let in the REPL.
Yeah, maybe, probably it would work without. I mean, I could do, I mean, what we do here is we give names to things, right? I mean, all the things we did, that was giving names. Most of them were functions, but it doesn't matter. It doesn't have to be a function. I could also do this languages equals, right, so I could just do this, and now it's, I mean, even in my code. So I just write it, and now I have a name for this thing. And now in the examples I could do whatever, insert Python false languages. Sorry, too much TypeScript. Right, and then yes, you can give names to things. Both in the REPL as well as in there. And what we haven't seen yet is like, I mean, all equations we have seen has always been top level, but of course in Haskell you can also have like local naming. So if you have a complicated function, sometimes you want to give a name to an intermediate result, and you can also do that. There are like two different constructs for that we will see soon. Okay. And of course it's complaining that because it's now a top level definition, it doesn't have type signature, so I should add that probably. Right. Okay, any more questions? So I think we should probably soon have another break, but I can do the new type stuff still.
New type, and then we have the actual syntax tree, I think.
Binary trees.
Binary trees, and then that, yeah.
Okay, so two ways to define data types that we have seen. Data and type. Data defines a completely new type with new constructors. Type is just gives a new name to an existing type. And there's one other way in Haskell, and that's called new type. And that's somewhat like a cross between the two. So new type is like data in the sense that it defines a completely new data type. But it's like type in the sense that the new data type will be like the same as an existing one. But okay.
Internal representation. Right?
Yes, so let's see. So if I write new type, I mean, first of all, the syntax is like with data. So I need constructor names. So for example, I can pick the constructor table. So I mean, okay, hang on. I should probably. So this you would already understand from yesterday, or you should. So I can define a new data type table. If I now don't just want table to be a new name for lists of pairs, but instead want a brand new data type, then we already know how to do this with data. Data keyword, name of the new data type parameters, and then a bunch of constructors. So yesterday we had two, this genesis block and block chain. Right, in this case I only have one constructor. I call it table. I mean, it doesn't have to be this same name. Maybe it would actually be better to call this make table. I mean, I always call, if I only have one constructor, I give it the same name as the type, but that is not a requirement. You can name it whatever you like. And some people also call it MK type name, so make a table. Right, and I only have, in this case, only one constructor, make table, and it has only one argument, this list of pairs. So now I have a perfectly new data type that's called table. And that's now not the same type as a list of pairs. It's a new type. And you could do that, but you already see the squiggles. And the problem with this is an efficiency problem, because each data constructor, basically, or each data thing, introduces a new level of indirection in the compiled code. So if I now use this type instead of my original type synonym for tables, it would work, but it would be slower because there is an additional indirection, because it always has to pattern match against this make table type. So therefore, there is a third way in Haskell to define new types for the special case that you only have exactly one constructor with one argument. So only one constructor with one argument. So in that case, you can replace the data keyword with new type. Semantically or syntax-wise, it's basically exactly the same. Whether I write new type or data, how I work with the type is exactly the same. The difference is just that at runtime, or like the compiler will remove all this fluff. And will just internally, it will be exactly represented like before, like a list of pairs, no additional indirection. So this is basically a safety measure for the user that you, I mean, so it helps the type checker to make sure that this is a new type and, I mean, its own distinct type. But the compiler will optimize all of that away, and in the end, the code, the runtime code, will be exactly the one we just wrote, as if it was a type synonym and not a new type. And the reason you do that is if you, I mean, we come to that in a bit, but for example, to like a layer of abstraction to hide away an implementation. So you could maybe later want to change your table type against a more efficient type, like a tree or hash map or whatever. And if you use our original approach, where it's open to the world, that the table is just a list of pairs, then you can't afterwards change the implementation, change it for something more efficient, because people may rely on your representation by using new type. And then, I mean, this alone is not enough. You must also hide like the constructor, but we can talk about how to do that. It's possible to basically encapsulate your implementation, and people only get this interface, and as long as you keep this interface, you can do whatever you like and change the implementation. So now, of course, if I do this, I get millions of errors, because now, I mean, it, for example, complains. So now a table is not any longer a list of pairs. It's like the runtime representation is the same, but for the type checker, it's a different type. So I can no longer write empty list here, because I'm supposed to write a table, not a list. And now those two things are no longer the same. So now I do have to use my constructor here. And I called it, I'm not sure. Let me call it table, but please remember it doesn't have to be the same name. So I renamed the constructor to table, but you can name it whatever you like, but it must be capital. Okay, and now here, now this also won't work anymore because, I mean, this is now on the right-hand side is a list, but expected is a table. And this here is not a list, it's now a table. So I can pattern match here to get to the x-axis, which is the list, and then here wrap it in the table constructor again. And so as you can see, everything gets somehow messier. But in principle, it's a mechanical thing I'm doing. If you do it, oh yeah, sorry. Now I probably, no, I think, no, I think I have to, hang on. LKV, yeah, I mean, it expects a list here, so I must extract the list somehow. So this is a bit bad. How do I do that? I mean, I think I need a where clause or something, or I must introduce record syntax.
I think record syntax is later. Maybe where will be?
Okay, I need a helper function now. I mean, I don't know whether see what the problem is. I mean, in this recursive case, the delete gives me a table, but at this point I now need a list. So I must turn a table into a list. I can use the table constructor to turn a list into a table, but at the moment I don't have a function to do the opposite. So let me just define one. Let me just define a function untable that takes a list of key value pairs and turns it into a table. And that I can easily define. No, other way around, sorry. Table. So I pattern match, I get my list, and it's this. So you don't have to do this. I mean, there are other ways we will see in a moment that you get that for free. But anyway, if once I have defined this function, I must plug that in here, untable. Yeah, now that compiles. And almost done. Only lookup left, nothing. Yeah, table. 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 Right, so lots of mess, but the good news is that this doesn't change because I'm just using the interface to define the languages, and the interface hasn't changed, just the implementation. So if I now reload and ask for, okay, I have to derive show for this new type. Sorry, where is it? There. Okay. So I do have my languages, and it looks almost exactly as before, but now it has this table constructor there. So you see it's somewhat of a pain to do this. I mean, before it was much easier to, I mean, logically it's exactly the same. I mean, you just at the right spots have to insert this new constructor, and at other spots you have to remove it. But it looks much messier. And therefore I mean it's a trade-off, right? So what you gain now is you have more type safety. So now you can't just mix lists of pairs and tables, it's different types now. And if you put this table stuff into its own module, I mean, we will talk about export later. But you can basically put this whole table stuff into its own module and only export the table itself, the type, but not the constructor. and then it's impossible for people using your module to fiddle with, to use these things directly. So they will have to use your interface to work with tables. And then later you can swap the implementation of the table with, for example, a balanced tree or red-black tree or whatever. So what you gain is type safety and the flexibility in future to change the implementation. What you lose is like simplicity. So it's a trade-off whether to use a type synonym or a new type.
Many of the libraries that are already in Haskell use this technique to hide the actual details of the implementation. So thanks to that, when you use the library, you can use it freely, and then they can optimize it, and you get all the gains without changing your code, right? And when you write a library for them, use yourself, you can do that. For then your apps, for example, you write some library to handle servers, and you hide the implementation, and then you can build like 45 different apps, and then you can optimize the library, and you don't have to change any code of those all for 45 apps, right?
Mm-hmm. Right, I just want to double check on the slides whether I missed anything important. So here was one remark that because the table type now has exactly one constructor, if we do something on table type, we also like pattern match on this table constructor. And here's just the new type versus data. So again, new type, you can only do new type if it's one constructor with one argument. But apart from that, it behaves like data. And it's, I mean, the advantage of new type is it guarantees the same runtime representation. So you don't pay a runtime cost for using new type. So you basically get these type level security for free. I mean, for free at runtime, not for free at implementation time, because you have to, it gets more complicated to write it. And data can have an arbitrary number of constructors and arguments, but it induces additional indirection and therefore inefficiency. Right, and I showed that, so functions on tables have to be adapted to wrap or unwrap the table constructor that I just showed you how to do. And what I just said, so I mean, we haven't talked about module exports yet, so you can exactly say the things you define in your module, which of those should be exported to other modules. And if you don't list it there, then you can restrict that, and that's how you would hide the implementation. Right, and then people can no longer look inside your type and see these list of pairs. Okay, so yes, there are, I think 3 more examples or something, but I suppose we should have another short break, at least 10 minutes.
Question?
Yes? Indirection is like with pointers or so, if you, I mean, the value, I mean, whatever, the actual data is somewhere in memory, and then you have like a pointer, like a memory address that points to the data, and maybe then you have a pointer that points to where you find the pointer that points to the data. So each such pointing step is called an indirection.
The processor has to go over all these pointers to get to the actual value. So if you can reduce them as much as possible, that's possible.
Mm-hmm.
Also, what's the difference between new type and the data in terms of functions? Because you say like when you introduce a new type, it's like you're creating the data constructor of the functions.
Right. Yeah.
So
it will be the same as you have to pattern match for one value because you know that it will be only one constructor. So when you're building the functions, you know that you will usually have like a single definition of function, single equation. That was the question.
Not really. You said like the data constructors are like functions.
Yeah.
So like in new type, are they also like the data constructor, new type also functions?
Yes. Yeah. New type and data behave exactly the same. I mean, like it looks exactly the same. There is this indirection thing, so it's more efficient to use a new type, but the way you program with it is exactly the same as with data.
So, like, you could write like all the Haskell code you want with a data with a single constructor, and then switch it to a new type, and in virtually all cases it should work like the same. So yeah, in this case the table was like a type constructor that has 2 inputs. So it was like a function that took 2 inputs to get the final type.
Okay, any other questions? Okay, yeah, let's say 10 minutes again.
Okay. Yeah. Final.
Right, let's continue. So 3 more examples, I think, and then we are done for today. So the first is a bit cryptocurrency, but not really. But I mean, it's called transaction. So we are defining a new data type. We call it transaction, and it only has one constructor. But that constructor has 3 arguments. So it wouldn't be possible to turn that into a new type. Remember, new type, one constructor, one argument. So we call the constructor transaction as well. But again, you could also call it whatever you like make transaction or whatever. And 3 arguments, amount, account, where for simplicity's sake, amount is just a synonym for int and account is just a synonym for string. So maybe let me just do this. So data transaction. And I don't know whether, so the slides they will all be in the repository, so you don't have to worry about tonight. Yes. So we always put the slides of the lectures into the same day into the repository. Okay, so one constructor. What was it? Amount, account. And I must tell it what amount and account are. So amount is just int and account is just string. Right, so far so good. And now, of course, I could, and in the slides, we also want to look at transactions. So we are deriving show. And I think in the slides, we also derive equality for transactions. Okay, let's reload. And now I can construct a transaction. So for example, whatever, send 100 ADA from me to Karina, whatever. Right, and I mean, something like that is very common, that you have types like this with one constructor and many arguments. For example, if you think of a user type, then it might be whatever, screen name and first name and last name and age and city of residence and nationality, and it would all be arguments to one constructor. So this is a common case. And typically what we want, given a transaction, we would like to extract these values. So we would like a function amount, or what's it called in the slides? Sorry, I just want to keep from to and amount. Oh yeah, before I come to that, I mean, again, because we have one constructor, functions that operate on transactions will typically have one equation where you pattern match on that one constructor. So if we want to extract the amount from a transaction, so following this pattern, we pattern match on amount from and to, and just return amount. So we see we don't need from and to, so we can replace those with underscores. So now we want from and to as well. And I mean, maybe this we haven't seen before. So I can combine several signatures if they are the same in one line. So this is the same as if I had just given 2 separate signatures. And let's define those quickly. So transaction from, transaction amount from to is from, and to transaction amount from to is to. So now I can again replace the arguments I don't need with underscores. Okay, like this. So now I can try it out. So I had this example transaction. I can give it a name if I want. So I can say tx equals this. So I indeed don't need the let anymore. And now I can try out tr amount of this transaction is 100, and tr from is Lars and tr2 is Karina. And this is, as I said, very common that that you have a data type like that with one constructor, many arguments, and then you often need these helper functions that extract one of the constructor arguments. And because that would be tedious to always do this by hand, there's a special syntax for that, so it's nothing new really, it's just to help you, and that's called record syntax. So data types like that with one constructor are called records. So the alternative way to write this is as follows. So this is now a new syntax. So instead of putting the arguments just after each other, you have these curly brackets, and then you give names to your arguments and give the type. So in our case, it's transaction amount is one name, and then you separate various ones with comma. Account. And normally you would align this, but okay. And now I can remove all of this. So the data type now is exactly the same as before. I mean, it more or less, I mean, it behaves the same. So it's again a data type with with one constructor, and the constructor has 3 arguments. But now I have named, using this so-called record syntax, I have named the arguments. And what I get from this is that the functions tr amount, tr from, and tr2 that I've before had to define by hand, I now get them for free. So they are now just defined by the compiler for me. So if I see I deleted these functions, my by hand definitions, and if I now reload and do this again, I get exactly the same results as before. So even though I now no longer explicitly defined tr amount, tr from, and tr2, this is now automatically I have these functions. So whenever I define a record type, then I for free get these so-called accessor functions for the record field, so-called fields. So the different constructor arguments are called fields, and they have a name, and I get these functions that extract the field with the given name. And I can also here in the I wrote this, my example transaction. So that's perfectly fine. I mean, as before, yeah. So even though it's now in record syntax, the old construction works as before. So I still have a constructor that just takes 3 arguments. So I can still work with this type exactly as I worked with it before. However, there is an alternative syntax for this. Now that we have record, so I could equivalently write it in a more like recordy form, where I write it like this: tr amount equals 100, tr from equals Lars, and tr from equals Karina. I thought I should. I'm sorry? Two. Yeah, sorry. Thank you. Right. So those 2 lines do exactly the same. The first one is obviously shorter, whereas the second one is more informative, because I don't, especially if I have many fields, I don't have to remember which field is what. And here I could also swap the order. So I could also write this. That would also be fine. Whereas if I do it in line 146, it would be a different transaction. I mean, there the order matters. It's basically positional arguments versus named arguments. Right, so that's, and you can also, oh yeah, and then there's a third thing. I'm not sure whether that's on the slide, but what you also can do is so-called record update syntax. So often you have a record like this transaction and you want to modify it. Maybe keep some of the fields but modify others. So I could now define a second transaction where, let's say, it's the same as this one but with a modified amount of 200. So I could use this record update syntax as follows. So I take my existing transaction and then I say tr amount equals 200. So this will basically create a copy of the tx. So it doesn't change the original tx. It creates a new record, a new value of type transaction, where all the fields that I don't explicitly name here are the same as of the original one. So if I reload this and ask for tr amount of tx prime, it's now 200. But from and to are the same as of tx. So that's called record update syntax. And you can also have more than one update in these curly brackets. So you can change more than just one field. You can update as many as you want. So this is, I mean, you wouldn't need that. I mean, you could do all these things without records. It's just more boilerplate and manual implementation. You always have these helper functions that you have to define and so on. So this is often, it's just to save you typing, basically. And these record types, I think in the lectures they will be very rare, but in real life they are all over the place. Because in real life you always have to deal with these things. I mean, if you look at Pluto's, the API, like there is a transaction type for Pluto's, for Cardano transactions, and it has like 10 of these fields. And then each of the fields is of a type that again has 10. And so, I mean, records are just all over the place. And as I said, like with users in a database or so. I mean, if you think of databases, record is a bit like a database table. So each column in the database table would correspond to a field. And you know how databases, SQL databases are everywhere. And therefore, for real-world programs, you have these annoyingly big records. Right, and it's relatively easy to work with them. I mean, there are still limitations to this. And in one of my favorite lectures ever of this course, I mean, we talk about that, so-called optics. But yeah, one can work relatively nicely with records in Haskell. So that's so that's records. I hope, did I mention everything? Yeah. Oh, okay. Let me just see, what does that do?
Actually makes the transaction.
Yeah, but only if the funds are there, right?
Yeah.
From old to old, right. Right, so now the idea is to write one non-trivial function using transactions. What's it called? Okay, so first there's another type synonym. Accounts is just a synonym for table from account to amount. So you can think of accounts now as, I mean, it's like a bank. So it knows for each account how much money is in that account. And now what's the function called? Process transaction. So given a transaction and accounts, it updates the accounts by, well, processing the transaction. Okay, and how do we write this? So we pattern match on the transaction, or we could pattern match on the transaction, but we don't have to because we have these accessors. So, I mean, I could write, normally I would write transaction, and maybe I should, I don't know, what's it in the slides? Yeah, it does that, okay, fine. So amount from 2. Alternatively, I could also not pattern match on it, and then if I want one of those three values, use the accessor functions to get them. So that's also like a matter of style or personal taste, and it depends on the situation. Okay, so now so the idea is I look up how much does from have, how much has to have, and then I update those values. So I subtract the amount from and add it to 2. But that only makes sense if from does have sufficient funds. So I want to check. And right, and now we combine lots of things that, so that's the one thing. And of course it could be that from or to doesn't even exist. Right. So they don't have a bank account yet. And then now using the functions that we defined during this lecture, we can do that relatively elegantly. And now I mentioned earlier that you can define like local variables or local names, give names to things. And one way to do that, so before we actually implement this, is let in. So the syntax is, it's let. Then I can have a bunch of definitions, so name, value, and then in, and I use it. So let's demonstrate. So I want to give names to the amount that F has and that T has. So I have this, so let's call it, I mean, F old, it's I think in the slide. So how much money does F have before the transaction? So we have this lookup, which takes a key. So the key is F. And I should give a name to the accounts. Let's call them, I don't know, accounts. I forgot that, so it's 2 arguments. This is the transaction, this is the accounts. Right, so look up F accounts. But this is now of type maybe, because it could be that it doesn't find. Let me just 1 second, sorry. Oh, I just see that this doesn't check whether you have enough funds in your.
No, it just returns 0.
No, but here it just, I mean, if it finds you, it doesn't check that you have sufficient funds.
Right, no.
Okay, fine.
If you're existing in the database, that's it.
Yes, it doesn't, but you can end up with negative amounts in your account.
Maybe we can modify live?
Yeah, maybe you can first do it like this and then modify it.
Yeah.
So sorry, I was mistaken earlier. This version doesn't check that you have sufficient funds. So the only thing it does check is whether, so this lookup, remember, can fail. And it returns a maybe. So if it finds your account, it returns the value in your account. But if it doesn't find you, it returns a nothing. But in that case, we just want to use 0. So, and we had this from maybe function earlier that turns a maybe into a non-maybe again, given the default value. So given the default value 0, right. So if it finds your account, it will return this value there, and if not, it will return 0. And we can do the same for 2. Sorry. Okay, and now I can use this. So this let in, so I let a bunch of definitions, and then in the in part I can use those now. So for my final result of what this should do, I can use this F old and this F2. So this is one way to define local variables, you could say. It's not really variables because they are not variable, they can't change, but give names to intermediate results. Right, and so now what do I want to do? I want to insert at F. So what is the new amount of F? It's the old amount, F old, minus the amount I'm transferring. And I want to insert T, what T had before, plus the amount into the original accounts. And it's not called T old, it should be called T old, sorry. It should of course be called T old, not whatever. Right. And we can try this. So let's define some example accounts. So whatever. insert, let's say, okay, so we have these accounts, and we had this transaction, this TX, where I sent 100 to Karina, and now I can try the process transaction with this example transaction and those example accounts, and it's correct, right? Yes. So I remember we had this convention that in our table we just shadow. If we insert, we don't remove existing keys. So now, I mean, the old values, I had 250 and Karina 1,000, and now I have 150, so 100 less, and Karina has 1,100. So that worked. And if instead, for example, if we try this non-existing case, so if we use a transaction where instead of to Karina, I send to Robertino, so I'm using record update syntax here to modify the transaction. Then it doesn't find Robertino in the original account, so it uses 0 now. And then I still end up with only 150, and Robertino now ends up with 100, even though he beforehand didn't appear. And as we just said, so there are a couple of problems with this. For example, what if you don't have the money, if sufficient money? And I mean, one could easily modify that if we, so this is the version in the slides, I think. So I think there are two things one should do. First of all, if it was me, I would check whether the amount is negative, and in that case, don't do anything. And otherwise, and secondly, okay, and otherwise this. And here I would check whether this the old amount of from is greater or equal to the amount to be transferred. And in that case, I would do what we did. And in the other case, I would also don't do anything. So I think this is actually a more sane version. So now if we change this to so I had 250, so if I now try to send 300 to Karina, oh yeah.
That was the old behavior, so we know that.
Yes, so in the old case, there would have been this bug that I end up with minus 50. And now after I reload it, it stays unchanged. And also if I try to transfer something negative, negative numbers in Haskell are a pain. You normally have to put them in parentheses. Then it also doesn't do anything. Yeah, so this is now a better version maybe. I think we can maybe just check in this example code as well that you have this version as well. I don't think we should change the slides for this, but okay, yeah, that was just, I mean, it's not an important example, just to give you an example, a little bit more complex example, how to work with these things and combine. Sorry, yeah, question? Yes, please.
Yes, you can just go one step back about the Karina's value. At some point I saw he had been sent like another 100 shillings and he had 1,100. Sorry, not shillings, he had 1,100. So when he's being sent another 300, I thought it should be 1,400, but I can see that.
Oh, because I started with the original accounts again. So let's see. If you look at what I tried, I mean, I always, when I tried these things, so for example, here, and that's a good question. So you are saying if I now do whatever tx prime, for example. Right. So first I'm sending her 100 and now I'm sending 200. So you are wondering why it's not for 1300 now. And the reason is that, I mean, it's similar to what we said before. My process transaction function doesn't change the existing accounts in place. It returns a new accounts value with the updated values. So the original accounts is still the original thing. So I didn't, it was the question we had earlier with writing to the file and updating and so on. So I haven't changed the original accounts, and in my examples I always applied it to the original accounts. If I want to do what you said, I would need to do this. Tx.
Name.
Oh yeah, name. So yeah, okay, fine. I can also name it. So if I can give this a name, for example, call it accounts prime. And now if I apply this function to accounts prime, okay, it doesn't matter.
No, because you're changing account.
Oh, sorry. Yes, let's do that again. So this. And now if I apply then I still don't get what you thought. Oh yeah, because I don't have enough money anymore. Let's do the same one twice. So so accounts prime is applying the original transaction to it. Ignore these warnings. And if I now do this again, but apply it to the result of the first computation, but the same transaction, so again 100, then now Karina has 1,200. So we have now 3 different values. I mean, we have the original accounts, then we process the transaction. The original value is still the same. We got a new value of type accounts where she has 100 more. And now if I take that one and apply the same transaction again, I get a third value of type accounts where she now has 200 more than in the beginning. But it's 3 independent values. We are not changing, modifying anything in place. We keep what we have and produce a new value. And that's very typical in functional programming and in Haskell. You also do get that in E. And there are, of course, millions of variations on trees, and this one has data in the leaves. So it's a binary tree with data in the leaves. So we have a tree with where the type of data in the tree is of type A. And we have 2 constructors. A tree can either be a leaf or a node. If it's a leaf, then it carries a value of type A. And if it's a node, then recursively it has a left child and a right child, again of type tree of A. And so I have 2 constructors, leaf and node, of these types. And because of what we said during the lecture today, typically a function operating on trees would have 2 equations, one for the leaf constructor, one for the node constructor. What is new now for this example, in contrast to, for example, lists, is that this is like the type we are defining appears twice in this constructor. I mean, with lists we had the cons case where it was head and tail, and the head was again a list, but it only appeared once. So in tree case, because both children are again trees, basically we get like a double recursion. And typically when we implement a function, we will call the function we are just defining recursively twice, once on the left child and once of the right child of a node. Let me just see. Okay, flatten. So let's do this quickly. what was it called? Just tree, right? Data tree A equals leaf A or node tree A. Let me just derive show. Okay. And now we could have an example tree. Let's say tree int. And what, I don't know. Let's try to, hang on. Don't want to make it too simple. Can you, what?
I can draw it in the...
Oh yeah, can you please draw it?
Yeah. How many...
Maybe 3 children, but like on the left, no, or I don't know. Something that's not too, like 4 children, 4 leaves, but at different heights, I mean not symmetric.
Okay. Now, give me the black one. Thank you.
Mm-hmm.
And so the first one.
Yeah, like this is fine, I think. 3 is enough. And then some integers.
And integers.
Ints. Uh-huh. Okay, so that tree, for example, how would we write this now in code? So the root of the tree is not a leaf, so we need the node constructor. Now we need the left child and the right child. The left child is just a leaf containing 7. So the leaf, it would be leaf 7. The right child, however, is again not again a node, so it's node. And that one now has left child 4 and right child 9. So leaf 4, leaf 9. Let's see. Yes. So this expression now would correspond to Robertino's picture there. And now we want to, as one example of one of 2 examples on trees, or function on trees, we want to define a flatten function that flattens the leaf values in a tree into a list, going from left to right. So flattening that tree should result in the list containing 7, 4, 9 in that order. Okay, so that's the idea, what we want to do. So flatten takes a tree with leaves of type A and returns a list of type A. And as now, I mean, it's supposed to be boring because it's always the same, that's the point. It should become instinctive. If somebody wakes up in the middle of the night and says, define a function on trees, you should immediately know that you need 2 equations, one for the leaf case, one for the node case. So how do we flatten a leaf? So what's the list of values contained in a leaf? Well, it's a list only containing that one value, that one A. And okay, so that case is easy. And how do we flatten a node that has a left and a right child? And we already know from the slide or from experience now that probably we will have to recursively call flatten on left and on right. And in this case, it's easy. So we have left child, right child. We recursively know how to flatten the left child and the right child, and so to turn them into lists. So now we have a list for the left child and a list for the right child, and in order to get the list for the complete tree, we just concatenate those 2 lists. So it's just flatten L plus plus flatten R. And we can try this on our example tree. And we indeed get 7 for 9 as expected. Okay? And I think there's a second example computing the height of a tree. So the height of a tree, I mean the height of a leaf is 0, and then the height of a node is the maximum of the height of the 2 children plus 1. So it's recursively defined. So in this case,
looks weirdly. This should be more like here.
Yes, so this would be 0, 1, 2. So if we do that properly, then in this case the height function should return 2. The height of that tree should be 2. Okay. Height of a tree is just an int. So, and again, we have two cases, leaf and node. So the height of a leaf is 0, and we don't care what the actual value at the leaf is. It just depends on the shape of the tree. And the height of a node with left and right child, where we already guess that we recursively have to somehow use the height of the left child and of the right child. And now given those two heights, what's the height of this, of the node itself? Well, I said it in words before, so it's the maximum of those two plus 1. And maximum in Haskell exists, so it's max, and it takes 2 arguments. And as long as you can compare the type for size, which you can, then that works. So this. So that just says what I said in words earlier. The height of a leaf is 0. The height of a node is the maximum of the height of the 2 children plus 1. So if we apply that to our example tree, we get 2, the right answer. You can just check the slides, flatten, height. Okay, so other questions to this? We will have many, many examples and exercises and so on about trees. I mean, trees are all over the place. This is just the first taste. Okay, if there are no questions, then we can come to the last example for today. Right. So until now, so we have seen, what was it? Bool, maybe pairs, forgot, lists, transactions, and trees, right? And they were all like somewhat different. So bool had 2 constructors, but was not recursive. Maybe had 2 constructors, was also not recursive, but it had arguments. The constructor, the just constructor has an argument. Lists, also 2 constructors, like maybe or bool, but it's a recursive data type. Then we had the transactions. They only had 1 constructor, 1 argument. Oh yeah, we had the tables. So the type synonym, so basically then 1 constructor, 1 argument, new type. Then trees now that have transactions, record syntax, so 1 constructor, many arguments. Now the trees, again, like with lists and maybe 2 constructors, but the interesting thing about trees is that they are double recursive because 2 of the arguments are trees again. And now finally we want to see an example with many constructors that you don't think it must be at most 2, because until now we have never seen a type with more than 2 constructors. And this is, I mean, one thing that Haskell is really, really good at. I mean, I believe it's good at everything, but where it really shines is like symbolic manipulation of expressions and DSLs, so-called domain-specific languages. So it's very easy to implement a new programming language in Haskell, at least experimentally, to play around with syntax to basically represent programs or expressions or something symbolic like that in Haskell. So that's where it's really like natural for. So the idea here is to have a data type that represents simple arithmetic expressions. 4 constructors. Let me just immediately do this because I have to do it anyway. So the first type of expression we call lit, and it takes an int as parameter. So that's an integer literal, something like 7. So that would be an expression. Then we want to be able to add to, sorry, we just want to get it right, yes. We want to be able to add 2 expressions. So this is a double recursive case. So given 2 expressions, we can add them. Then we want to be able to negate an expression. So this is a simple recursive case. where we have a recursive argument, but only one. And finally, we want to have something like an if statement, so taking 3 expressions. So the idea is, if the first expression is 0, then this is the second expression, and if not, then it's the third one. Okay. And is there an example? I don't know. So now we should define a cool expression. Whatever, if 0 lit 7 at nec 2 lit 5 lit 999. And I should derive show, so we can see it. What now? Oh yeah, lit. I forgot the lit, sorry. Okay. So this is an expression. So expression is not a number, I mean it's an expression. So the idea is you have whatever, I mean I don't know. Maybe you are writing a parser for a programming language and you are passing like an expression, like your programming language, you can do stuff like plus and minus and so on, and you are passing that and you want a syntax tree of the result. So this would be that. And of course, but our intuition of course is that you should be able to evaluate expressions, to actually compute them. So is that the example? I hope it's the example. Yeah, right. And so I mean here we basically, this is now a type, and I would normally format it differently. Everything is nice and neat. So this is a type with 4 constructors now, and basically almost everything we have seen today is like combined in this one. So the lit constructor takes 1 argument, but it's not recursive. Then we have this add, which is double recursive, so it's a bit like node in a tree. We have this nec, which is single recursive, so it's a bit like the tail of a list. And then this if 0, which is even triple recursive. I mean, I don't think that word exists, but right. Okay. And now, of course, we know, I mean, even though we just saw this type for the first time, if we write functions on this expression type, we expect 4 equations. 1 for lit, 1 for add, 1 for nec, 1 for if 0. And we expect that this one will not be recursive. This will have 2 recursive calls, this 1 recursive call, and this even 3 recursive calls. And as just the last example for today, let's just write an evaluator. So given such an expression, it just computes it in the obvious way. I mean, with the obvious meanings of add and nec and if 0. So let's try this. And maybe before, we should see what should be the result, so that we can be proud if it comes out like that. So if 0, so the literal 7 is not 0. So this is false. So this here should be ignored. I actually wanted to have it more interesting and the other way around. So let me just put the lit 999 there instead of there. Okay. It doesn't matter, but I just wanted to have an interesting example. So 7 is not 0. So this is ignored, and instead this is evaluated. And there we add the negation of 2, so minus 2 and 5. So the result of this whole thing should be 3. So if we write our evaluator and we get 3, it should be good, a good end for today. So eval takes an expression and returns an int. And we need these 4 cases. So let's do one by one. So if we have a literal, that's already an integer, where evaluating a literal just evaluates to itself. So evaluating lit 999 is just 999. So next, sorry. So the next case is add. Well, how do we evaluate an addition? We just recursively evaluate x and y and then add them. So it's eval x plus eval y. So how do we evaluate neg, the negation? Well, we just recursively evaluate x, and now we must negate this. And this is now again one of these painful things. I think this won't work. Or will it? It actually will, I think. For some reason, the Haskell parser has a problem with like unary minus signs. So sometimes it doesn't work and you need parentheses and so on. But in this case, it does work. So.
Yeah, because you have a parenthesis, I think.
Ah, yeah, okay. Yeah, anyway. Let's not question our luck. And finally, if 0, x, y, z. So what do we do here? Well, we must first evaluate the x and see whether it's 0 or not. So we can use guards actually. So we can say eval x is 0. So in that case, we evaluate y. And in the other case, we evaluate z. And let's try it. Yeah, so we get 3. So yes, that's maybe the last example, like to show you all the cases. And basically the point of today's lecture is first to show you lots and lots of, first to introduce you to some of the most common Haskell data types, bool, maybe lists, pairs. And secondly, to show you that typically if you define a function operating on some type, then the definition of that function will closely follow the structure of the type. So we'll typically have one equation per constructor, and then whether the function is recursive or not will depend on whether the data type is recursive or not. And that's not always like that. I mean, there are many exceptions, but this is like the standard design pattern. So basically, normally you should first try this, and then there may be a reason why it doesn't work or why something else is better. But this is like the default, like not think about it, just start rightly implementing it. So yes, and we saw this last example with expressions, just a more complex example with more constructors, various number of arguments in the constructors and so on. Okay, yeah, and that's that. So do we have any questions? Yes?
Could you change the type of expression to like double?
I mean, of course, I could now just replace every int by double, but that's not what you mean, I suppose. You want to make it parametric in? Yes, I could. I could, for example, say expression A, and then replace that by A, and then need this type parameter everywhere. And then if I do this, so this is still an expression, let's say double from, I don't mind. And now this evaluator, now I get two errors. One is the plus, because I need to know how to add these numbers, so it must be something I can add. And in Haskell there's a type class for that, num. So that's these numeric types that were briefly mentioned yesterday. So both int and double are instances of that. So this makes that error go away, and this one for negation. So the num class knows how to add and how to negate. And now I still have this error that I also need to be able to compare for equality. So I need an additional constraint A. But given that, it still works, and now it's an expression double, and I get 3.0. Yes. So you could make that parametric in the type of literals. And of course, you can make it arbitrarily complex. You could have different data types and whatever. It's just right. Are there other questions?
Tomorrow we'll go more in depth in that subject.
In type classes? Yeah. Okay.
How do you walk down actually?
I'm sorry?
How do you walk down? Like you can just change every leaf to another number or another.
F map for trees.
Fmap for trees. This is simple. So let's call it tree map. Given a function from A to B, and the tree of A's, turn it into a tree of B's, where I apply the given function to each leaf value. So if I have a leaf, I get a leaf where I have applied the function to that value. Tree map. And if I have a node, I just recursively tree map the same function over the left child and the right child. And if we take our example tree and tree map +1 over our example tree, then we increase each leaf by 1.
Or we can show to make them like strings.
Yes, or we can map show over it and turn the integers into strings. So it doesn't have to be the same type. A and B can be different types. Are there other questions?
How was growing before?
Sorry? Growing?
Like insert for trees.
Oh yeah, that's isn't that an exercise?
Yeah, I think
Yeah.
Yeah.
it's already published the exercise. Oh, we can start it.
Okay, then maybe it's enough for today,
Yeah, that's it.
except if there are more questions, but yeah, should. And you should start doing the exercises.
Yeah, they already published the exercises. Same way, you click the link and you get the whole setup. And if you have any questions now or like at night, write and